The CP8102 is a dual-input, single-output control module, part of Barbara Coleman's System 8000. It's usable wherever proportional control or proportional control with reset are required. Applications for which the CP8102 is suitable include hot water or chilled water reset control, other types of reset control, and single-input temperature and relative humidity control. The module itself is track-mounted on a provided 3 7/8 by 11-inch plastic track. And it'll operate at ambient temperatures between +40 and +135 degrees Fahrenheit. It consists of 2 sensor input bridges, Bridge A, the control sensor, and Bridge B, the reset sensor, and an operational amplifier which generates a 1 to 15 volt DC control signal. Externally, the following terminals and adjustments are accessible. ISA, ISA. 2 input terminals for sensor A, the control sensor. The sensor itself may be any 1000 ohm Balco element. For example, TS8201, the duct immersion sensor. Whatever the sensor, the variable being measured is the one being controlled. ISB, ISB. A second pair of input sensor terminals, this time inputting to Bridge B, the reset bridge. A variation at sensor B results in a change in set point A. A typical sensor applied to B would be the outdoor air sensor, TS8501. AB1, auxiliary bridge input 1. This terminal permits the addition of remote set point adjusters or additional sensor signals through an external bridge module. It will accept a nominal 3.1 volt DC signal. AB2 and AB3, auxiliary bridge inputs 2 and 3. These terminals can also serve as signal inputs, but their primary function is easy disable of Bridge B when no reset is required. Removal of the factory installed jumper disables the Bridge B output. Tie. This is a non-functional terminal. +20. This is a pair of identical power input terminals. The CP8102 requires 20 volts DC at 23 milliamps to operate. Either terminal can be used, with the power source usually a System 8000 controlled device. 6.2. This is a power output terminal used to power remote set point adjusters or external bridges. It's rated at +6.2 volts DC at 7 milliamps. SW. This is the same as the +6.2 terminal, but can be isolated by cutting jumper strap J7, visible here. It functions then as a summer-winter switching terminal, with the switching of the controller action from direct to reverse acting and back based on some specific condition. An example of this will be given later. OP1, 2 identical output terminals. The output is a 1 to 15 volt DC controller signal. Up to 6 System 8000 controlled devices can be operated directly on this signal. And common. These 2 terminals serve as reference for the various positive voltages already referred to. The upper common can be isolated by cutting jumper strap J8 located here, and is then usable for controller switching, as was mentioned for the SW terminal. The cover accessible adjustments are Set point A. This is the set point for control bridge A. It's adjustable from 20 to 120 degrees Fahrenheit, but whatever its setting, that is the variable value the controller attempts to maintain. Calibration A. This is an access port allowing controller recalibration without removing the cover. Below is the calibration pot for bridge A. Set point B. Adjustment point for bridge B, the reset bridge. This is also adjustable from 20 to 120 degrees Fahrenheit. But it's only functional when the jumper wire between terminals AB2 and AB3 is present. CalPot B allows for recalibration of bridge B. Ratio adjustment B. This variable adjustment determines the effect of sensor B in reset applications and is adjustable from 0.5 to 25, representing the ratio of bridge B to A, with A always taken as 1. For example, a setting of 0.5 means B to A 0.5 to 1, or for every 1/2 degree Fahrenheit change at sensor B, the effect on the controller will be a reset of set point A by 1 degree. Another example, with the setting on the ratio pot of 25, it would be read as 25 to 1 B to A, and now it would take a 25 degree change at sensor B to give the same 1 degree reset of set point A. The ratio adjustment pot functions only when bridge B is operational. Finally, throttling range. This is a variably adjustable pot allowing a 2 to 10 degree Fahrenheit throttling range. Additional adjustments are beneath the cover. Set point A jumpers. There are 2 jumpers associated with set point A. The first one, the brown one shown here, is jumper J1. This permits disabling of set point A while keeping bridge A intact. By moving this jumper from its factory position, J1 to pin JC1, over to pin JC2, the set point adjuster itself is bypassed. If desired, bridge A can also be disabled by removing the center tap wire from the set point pot from its pin, which is marked A. Also associated with set point A is the calibration pot shown here. Set point B can also be disabled, as well as bridge B disabled, through the same procedure. However, the standard disable procedure for set point B is to use the AB2, AB3 jumper removal. Set point B also has its own calibration pot. Calibration will be discussed later. Throttling range. While most applications will use a 2 to 10 degree throttling range, if a wider throttling range is desired, it is available through a fixed throttling range selection. By moving this jumper, jumper JC9, from its standard position to any one of these 4 pins, other wider throttling ranges can be selected. If none of these are suitable, an auxiliary resistor may be placed here and other throttling ranges achieved. The action jumpers. two pair of jumpers in the upper right-hand corner of the controller determine both its action, direct or reverse action, and its reset, direct or reverse reset. The jumpers as shown here are in the factory position. That provides for direct action with reverse reset. The red jumpers determine the action of the controller. When they are parallel, as they are here, the controller is direct acting. By removing those jumpers from their pins and crossing them, the controller is made reverse acting. The second set of jumpers, in combination with the first, determine the reset of the controller. Remember, if bridge B has been disabled, all reset functions are also disabled, so these jumpers serve no function at that time. A simple rule that determines the reset of this controller is as follows. When the positioning of the two jumper pairs is the same, the reset is reverse. An example of reverse reset is hot water reset, which we'll describe later. When the position of the two jumper pairs is different, as we see it here, then the reset of the controller is direct. For example, direct reset of cooling based on outside air. To review the action jumpers, let's look at this chart. Note that J3 and J4, the upper jumper pair, is parallel. That means that bridge A and the controller are direct acting. Bridge B also is parallel. However, the important point to note here is when the B jumpers are the same as the A jumpers, the reset effect is reverse. This diagram shows a change. Now the bridge A jumpers are crossed, giving us reverse action for the controller. Note the bridge B jumpers have not changed. Now the two pairs are not the same. The result, the controller has direct reset. This diagram illustrates direct action. Note that as the variable, in this case temperature, increases, the voltage signal from the controller also increases. One other thing to note, even though each controller has a wide output voltage, in this diagram from 2 to 15 volts, the throttling range adjustment on the controller is much more limited. It refers to a 3-volt change, as illustrated here, from 6 to 9 volts. This diagram illustrates reverse action. The controller signal is still increasing, but now it increases with a decreasing variable. So variable decrease, controller signal increase, reverse action. There are 4 possible combinations of action and reset with the CP8102. The parallel lines here and here represent the 2 sets of action jumpers. Remember, parallel indicates direct. Since the upper pair is parallel, the controller itself is direct acting. Because both sets match, the reset is reverse. This example is the standard factory position for these jumpers. This is the second possibility. Since the first pair is still parallel, the controller is still direct acting. However, the 2 pair no longer match, so the reset is now direct. The third example shows a change in the upper pair. It's now crossed. That means the controller is reverse acting. Since the lower pair now matches the upper, we once again have reverse reset. The final combination shows a reverse acting controller as indicated by the crossed upper jumpers, and since the two pair no longer match, direct reset. Remember the rule: when the two pair of action jumpers do not match, we have direct reset. When the two pair do match, we have reverse reset. When the CP8102 is used as a single input controller, the control sensor will be wired through its two leads to terminals ISA, ISA. The details on wire length and wire gauge are contained in the electronics section of our green catalog. When the controller is used as a dual input, that is, with a secondary input for reset, that secondary sensor is wired to ISB, ISB. The wiring between the controller and control devices is as follows. At plus 20, a red lead indicating incoming 20 volts DC from the one or more controlled devices. At OP1, a yellow lead indicating the 1 to 15 volt DC signal outgoing from the controller to the controlled device. And at the lower common, a blue lead indicating reference for the voltages already mentioned. Once again, red, 20 volts DC being supplied by the controlled device. Yellow, 1 to 15 volt DC signal coming from the controller. And blue, our common or reference for the voltages. Calibration of the CP8102 is similar to that of any other proportional controller. There are 4 basic steps. Determine the variable ambient at the sensor. Set the set point adjuster equal to that variable value. Adjust the controller output to the desired value. That adjustment is usually done through some calibration device. Finally, restore the set point to the desired value, which may be very different from the ambient value at that time. Applying these rules to the CP8102, if an auxiliary bridge and/or input B are being used, disable them and then begin calibration with input A. Adjust the throttling range to the desired value for the application, or if not yet known, adjust to 3. Measure the variable at A and adjust the set point equal to it. If for any reason this is not possible, replace the sensor with a precision plus or minus 1% 1000 ohm resistor and set the set point equal to 70 degrees Fahrenheit. If a remote set point adjuster is being used, set point A should have been disabled and the adjustment is made at the remote set point adjuster. Measure the output signal across OP1 and common with a standard voltmeter. Standard calibration voltage is 7.5, and in fact the CP8102 is factory calibrated. In this case, the voltage is far from 7.5, so it will be necessary to adjust the calibration pot. Turn the pot clockwise or counterclockwise until the desired voltage is attained. If input A is the only sensor being used, we would now restore set point A to the desired value, and that completes our calibration. However, if there is a B input, leave the set point A at the ambient and now restore input B by adding the AB2, AB3 jumper. Then repeat the steps described for the calibration of input A, with one addition. Whatever the ratio required for the application, during calibration, the ratio adjuster must be set at 1. Then, following calibration, it can be readjusted to the desired ratio. If an additional sensor is being input through a multifunction bridge at AB1, that will remain off until B is calibrated. Then that multifunction bridge input will be restored and the bridge itself will be calibrated. In all cases, we calibrate to the same output voltage. In this example, the standard 7.5 volts DC. The option shown in this diagram illustrates summer-winter switching of the CP8102. The purpose of this option is to allow a change in action of the controller based on some external variable, such as outside air temperature. The setup is as follows. Jumper J7 and jumper J8 must both be cut. J7 disconnects the 6.2 volt terminal from the summer-winter terminal. Jumper J8 disconnects the upper common from the lower common terminal. With these two jumpers cut, power to the internal bridges of the CP8102 is also cut. That power will be restored through the use of an external double-pole, double-throw switch. What activates this switch, whether it be manual operation or automatic based on some variable change, will be determined by the individual application. The wiring is as follows. One side of the double-pole, double-throw switch is wired to terminal 6.2. The other side to the lower common. Then the center poles of the switch are wired one to the SW terminal and the other to the upper common terminal. As shown here, when the switch is thrown to the right, we restore the connection between 6.2 volts and the SW terminal, the lower common, and the upper common. Whatever arrangement of action jumpers we set on the controller, that now determines the action of the controller. However, when the switch makes in the opposite direction, now SW is connected to common, and the upper common will connect to 6.2 volts. The result? The action of the controller is reversed. In terms of any reset for the controller, The relationship between the two action jumpers does not change, so whatever reset was originally selected is maintained. This diagram illustrates the option of remote set point adjustment with the CP8102. A typical remote set point adjuster used for this would be the AD8122. It has an adjustment range of 20 to 120 degrees, the same as the set point adjustment range for the local set point adjuster. However, other set point adjusters may be used. The wiring is as follows. Any remote set point adjuster has 3 color-coded leads: red, yellow, and blue. In this case, the red lead will be wired back to the controller at the 6.2 volt terminal. That provides the power for the operation of the remote set point adjuster. The blue lead is wired back to our reference, the lower common. Then the signal generated by the remote set point adjuster enters the controller at terminal AB1. One important thing to note, whenever we use the remote set point adjuster, its polarity must match that of the controller. Look at the highlighted action jumpers. These action jumpers indicate the polarity of the A set point adjuster, or A bridge, and the action of the controller. This controller is direct acting. That means that the red lead must attach to 6.2 volts and the blue to common. By the way, don't forget to disable the local set point adjuster. Remember, take jumper J1 and move it from pin JC1 to pin JC2. In this example, a reverse acting controller is being used. Note the action jumpers are crossed, meaning the controller is reverse acting. Now let's look at the wiring of a remote set point adjuster. This time, the red lead is wired to the lower common, and the blue lead is wired to 6.2. The action of the controller has been reversed, and to match that, the polarity of the remote set point adjuster has been reversed. In terms of its signal, however, the wiring is the same to terminal AB1. This diagram illustrates the option of adjustable night setback. It can be used whenever the B input of the CP8102 is not required for reset. A 1,000 ohm plus or minus 1% fixed resistor is installed across terminals ISB. The jumper normally installed between AB2 and AB3 has been replaced with leads going to some sort of mechanical or electronic time clock. That clock will close contact, completing this bridge when we want the setback. The amount of setback will be determined by the setting on set point B as follows. When set point B is set at 70 degrees, there will be no setback. However, if we move it down to 65, that will create a 5-degree setback in whatever the controller set point is. For example, if the controller set point is 72 degrees, when the time clock is engaged, and if set point B is set at 65, we will get a 5-degree reduction in that set point. The set point will then drop from 72 to 67 degrees. Further reductions in set point B will result in greater setback. In addition, If set point B is set above 70, that will create a set forward effect in set point A. Finally, the ratio adjustment for the controller must be set at 1 for this application. And the type of reset required, as determined by the action jumpers, must be reverse reset. In this example of reset, ISB is not available. Instead, a fixed resistor is used in a circuit made and broken by a time clock between AB1 and either 6.2 volts or common. The arrangement is as follows. To offset the set point upward, that is a higher set point, the time clock will close between AB1 and 6.2 volts. To set the set point back or downward, the time clock will close between AB1 and common. This chart shows the relationship between degrees of offset in Celsius or Fahrenheit and the resistance value for the resistor in the circuit. For a typical 10-degree offset, a 1.0 meg-ohm resistor is required. One of the most common applications for the CP8102 is outdoor reset of hot water. The demonstration board shows a sensor, the TS8201, which would be used to measure the hot water temperature, usually in a liquid line. When used in that manner, a well is necessary. Since the hot water temperature is our control variable, this sensor must be wired to the ISA terminals of the controller. Outdoor air, our resetting medium, is measured by the TS8501. The outside air temperature, as represented by the signal input at ISB, serves to reset the hot water set point. We'll work out an example that will give us values for the controller settings. Let's say that the design engineer for a building has required that 180-degree Fahrenheit hot water be available when the outside air temperature is at its design temperature, or in this example, 0 degrees Fahrenheit. The design temperature is some low temperature, or if we're talking about cooling, some high temperature that is maintained over a period of time. It's not the absolute lowest or absolute highest temperature. The engineer will also determine a fade-out temperature, that is, some resetting variable temperature, in this case 60 degrees outside air, at which we're no longer interested in any hot water reset. In this case, we want a 90-degree hot water temperature when we reach 60 degrees outside air. Using these two sets of values, we can now determine the settings for our controller. Set point A and set point B are typically taken to be the lowest values on the hot water reset. However, they can be any combination of values from the reset schedule that are programmable through the two set points. In this case, we've taken the hot water temperature of 90 degrees when the outside air temperature is 60 degrees as our set points A and B. The ratio setting, as always, will be the relationship of B to A. In this case, the change in variable from the design temperature to the fade-out temperature for the outside air was from 0 to 60 degrees, a change of 60. The change at A was from a design hot water temperature of 180 down to 90, a change of 90 degrees. Our ratio then is 60 to 90, or 0.67. We would adjust the ratio dial to read 0.67. Controller throttling range. What the actual controller throttling range should be will be determined by the actual equipment and cannot be determined beforehand. However, a general rule of thumb is for smaller hot water systems, 10 degrees throttling range. For larger systems, which will respond more slowly, 20 degrees. System throttling range. System throttling range is not an actual setting on the controller. However, it's directly related to controller throttling range. Remember, whatever the controller throttling range, that change in variable will give us a 3-volt change in controller output signal. If the entire hot water system can respond to that 3-volt change, and in fact requires only a 3-volt change for full response, then the system throttling range and the controller throttling range are the same, as shown here. However, if the system responds to less than 3 volts or more than 3 volts, then the system throttling range will be less or greater than the controller throttling range. Let's take a look at 2 examples of system layout. In this example, our CP8102 is controlling a 3-way hot water mixing valve, which in turn supplies water to finned radiation. With this valve, with no signal coming from the controller, our hot water supply, directly from a boiler or converter, is at 100%. In other words, this port is full open. This return water supply, or cooler water, will be fully closed. However, as the temperature of the water being supplied to the finned radiation rises, our controller will issue a signal causing this hot water supply port to close down and the return water port to open up. Since as the temperature of the hot water increases, we want this control device to respond, we require a rising controller signal. Hot water signal up, voltage signal up. That's direct action. Further, since we're controlling only one valve, a 3-volt signal change will get full response out of this system. Our controller throttling range then, whatever it is, will be the same as the system throttling range. Here's another example. This time our 2-input controller is controlling 2 steam supply valves providing steam inlet to a hot water converter. The output of the converter is the hot water we're going to use for some purpose. The controller is sensing that hot water output temperature. Both of these valves are normally closed. That means as the hot water temperature rises, we want to allow those valves to go toward closure. A falling controller signal will allow us to do that. This time, as the temperature rises, we want our signal to drop. Therefore, a reverse acting controller is required. In addition, we have 2 devices to control this time instead of 1. Each will require a 3-volt signal change for full response. 3 volts, 3 volts, a total voltage change of 6. That's 2 times whatever the controller throttling range is. In this example, the system throttling range will be twice the controller throttling range. Based on our example, set point A should be set at 90 degrees, set point B at 60 degrees. Our ratio was determined to be 0.67 as set here, and the controller throttling range 10 degrees. Under the cover, The factory positioned action jumpers give us direct action with reverse reset. If the hot water valve or valves we're trying to control are normally open, then the factory jumper arrangement is satisfactory. With the red jumpers parallel, our controller is direct acting, and as the hot water temperature rises, our signal will rise to drive the normally open valve closed. With the second pair of jumpers also parallel, we have reverse reset. As the outside air temperature drops, that will reset the hot water set point upward. If our application requires normally closed valving, then just the reverse is required for control. Now our controller is reverse acting. As the hot water temperature rises, our signal will fall, allowing a normally closed valve to go closed. However, we still want reverse reset, so the second pair of jumpers must be readjusted to match the first. Remember, when the two jumper pairs match one another, the reset is reverse. When the two pairs are different, the reset is direct. Hot water reset, based on outside air temperature, is an example of reverse reset. For further information on the CP8102 and its applications, consult your local Barber-Coleman supplier, our green catalog, the general instruction sheet for the CP8102, or Engineering Bulletin 111.